Now I would like to introduce David Iagaru, who is from the Remote Sensing Technology Institute at the DLR and the Department of Applied Mathematics at the École Polytechnique in Paris. And he'll be presenting model-independent computational performance bounds for super-resolution algorithms. Welcome, we're looking forward to your talk.
So, good morning, everyone. Let me present you performance bounds for reliability and hallucination risk in remote sensing super-resolution. Okay, first let me introduce you shortly the inverse problem framework that our work is based on. So you consider some source, x, that is forwarded to some measurement, y, through some forward model that is given, f. You can consider the set of plausible sources, which we call M1 here, the set of realistic sources. And you can consider as well the forwarded version, M2. So the set of realistic measurements. The problem can be stated as follows. You're given some measurement y, and you try to recover the source that this measurement is from, up to some noise. To do that, to tackle this kind of inverse problems, people use models. There are many kinds, like deep neural networks, optimization-based, or many others. This mathematical description includes many kinds of problems, like remote sensing super-resolution, which will be the focus of our work, MRI acceleration, and microscopy as well. And you might think, OK, I will apply my deep neural network. It has been proven to be a universal approximator, so it might have arbitrarily high precision. But you might also think that there exist some performance bounds that are inherent to the problem. And yes, this can be the case. To see why, let me show you some cartoon example. So here you consider the set of plausible signals, which consists in this 3D torus. And the forward model maps some point in this torus to its 2D position. So the problem can be stated as follows. You're given this 2D position y, and you're trying to recover the point in the torus that corresponds to the 2D position. And you can see that you cannot do it well because the problem is ill-posed. You can see that for the same 2D position, you can have very different possibilities. So to quantify this ill-posedness, we introduce this feasible set, Fy here, for one given measurement. It corresponds to all the sources that can be mapped to this measurement up to some noise. OK, how to implement this idea in practice? So you're given a data set, which consists of pair of source measurements, where the measurement corresponds to the source. And on this data set, for each measurement, you can find all the sources that corresponds to it up to some noise. And so that way you can have some finite approximation of the feasible set. And you can reindex the data set correspondingly. And as usual, people define some average error, usually to train some model. They use some distance here. It can be L2, L1. It can be many other things. I will detail this a bit in some slides. It better be semantically relevant to your problem. It simply needs here to verify the triangle inequality for our inequalities to hold. And you may wonder, can the average error be arbitrarily small? And as you might have understood, it might not be the case, since you can have understood that through the example I showed with the 3D torus. Why does this happen? So you can define this quantity that we call the kernel size, like this. Basically, you measure the distances between 2 points that are in the same feasible set. And you can prove that the average error is lower bounded by half of this kernel size. Why is it interesting? This is a data set specific bound. So basically, you have a data set. You can get directly this bound that quantifies the ill-posedness of your problem. This is a forward problem inherent in the way that you can use any decoder this applies. And let me detail shortly potential usages. So for instance, you're in a training procedure, you see that your loss goes very close to your lower bound, but you still have 3,000 epochs, a lot of epochs. So you might want to stop the training because you know that the optimization won't lead to better average error. This can also be used as an uncertainty quantification metric because this is inherent to the problem and you cannot do better than that. Okay, the previous lower bound might be a bit long to compute if you have some hard inverse problem. However, I present here some proxy where you need some linear inverse problem, and for simplicity, I consider additive noise. And to compute this proxy, for each source, you add the symmetric of the source. So the symmetric, I mean, you subtract 2 times the kernel projection of the source. And then you can compute the symmetric kernel size here, which is defined in this equation. And it lower bounds the average error. I said this is a proxy because it assumes that this symmetric point is realistic, is a viable source. It is not always the case, but this lower bound can give a good idea of what are your performance limits. So you can use it the same way as the previous average kernel size. And yes, the computation is cheaper because you don't need to compute the approximate feasible sets. So now, more interesting part, how can you implement this in remote sensing, super resolution? So we did that. We consider high-resolution images that are from the naive dataset, so 1 meter ground sampling distance. The overall dataset covers, let's say, a surface equivalent of 1/3 of Germany, which is quite big. Depends on the application. You consider the corresponding low-resolution images that has S meters GSD for different scales. We first tackle 2, 4, and 8 as scales for super resolution. And we consider this approximate forward model of downsampling, which consists in Gaussian blurring and bilinear downsampling. And to evaluate the performance of any model, we use these 3 metrics first. So L1, the base of norm, which is some metric computed based on some wavelet coefficient computation, and some distance derived from the SSIM. And if you directly want to implement the idea, if you directly want to look into the feasible sets, as I described before, theoretically, you cannot do it if you look image-wise, because you might get trivial feasible sets, and you might not get something meaningful. So we split the images into patches, and for each detail, each patch, we look into the corresponding feasible set. And then you can compute the lower bounds patch-wise and aggregate them over each image and over the dataset. Okay, so what do you obtain when you do this? One first experiment, you look at the kernel size, how it evolves across scales. We did it with different distance metrics, and without any surprise, the lower bound increases when the scale increases because because of more and more impulse, like in the low resolution image, you lose more and more details, which is expected. And you may wonder when this is still viable semantically. We can see this through different examples. So here is a forest patch. You can see that for scales 2 and 4, you don't miss that many details. A bit more for the scale 4, you might miss some shadows between trees, but it might not be that important depending on your application. And for the scale 8, here you can see that you can miss a lot of details. You can look at the same kind of things on urban area. For scales 2 and 4, you only get 1 element in the feasible set. And for the scale 8, you can get 2 different building structures, which can matter. This is not universal, but on this example, you can see that you might not be able to do good super resolution on the scale 8. And then you might wonder, okay, you gave a lower bound, but how sharp is it? When you look at a good performing, relatively good performing model, you compare this performance to the lower bounds, you see that the lower bound is quite sharp. You can see it here. And one other thing is that the kernel size can largely depend on the semantic class you're considering. So for instance, here, the forest data are grouped under low error, the urban data under high error, and you might observe similar kinds of groupings if you consider a specific data set. And I told you you might interpret it as an uncertainty quantification metric. So some students we supervised compared this kernel size to classical uncertainty quantification metrics. And they observed some correlation that you can see here between the kernel projection and the standard deviation of ensemble prediction on this low resolution image for super resolution. Yes. Some references we used, and thank you for your attention.
Thank you, David. Are there any questions? Okay, well, maybe then I can ask something. Especially like this last slide that you showed regarding the correlation with uncertainty metrics as well made me wonder if you can use these performance bounds to flag images or events or something like this where the hallucination risk of these models is too high to then do reliable decision making. Like, would that be a potential application of this?
Yes, you can totally do that. If in your application you know some threshold of the error where it becomes problematic, you can directly use use a threshold filter. If you don't know it, you might look into the highest error and look into semantically what it gives, because hallucination is a semantic phenomenon.
Yeah. Okay. And maybe I can ask like a follow-up question. I'm from I do a lot of cell imaging. So have you tried is this in theory applicable to these types of histological images, for example, as well? Because we might also be interested in super resolution.
So in other kind of images?
Yeah, like if you image cells or something like that. Have you looked into this at all, or?
So we looked into MRI scans, MRI acceleration, and we also looked into some cartoon example of some MNIST data, but this is another work. This is not directly the lower bounds I described here, but the same framework.
Okay.
So the feasible sets, etc.
Fantastic. Maybe we can discuss later a little bit.
It is on archive, if I can show.
Perfect. Thank you. Thanks again for your talk.